Welcome to the 19th lecture of this series of lecture on basic building blocks of microwave engineering. Now, we have seen the microwave tubes and tube based amplifiers. Now, solid state devices also can make the oscillators and amplifiers. So, we will see a diode based oscillator very popular in amongst microwave engineers, that is called GUN diode, but remember the spelling GUNN, it is not GUN. It is a diode with having negative resistance. It was invented by J.B. Gunn in 1963, that is why the name GUN diode. It is a low power oscillator in microwave transmitter. Local oscillators in microwave receiver front ends almost invariably use this GUN diode, and in our laboratory microwave signal we can get from GUN diode, and nowadays you see the reflex klystron that is generally GUN diode is much cheaper. So, we use it, only problem is its power is not much, but most of the experiments can be done with this GUN diode, but there are some experiments where we require high power, particularly antenna experiments, there we prefer to have a klystron based source, but it is a very good source of microwave signal in laboratory. So, you look at the GUN diode, if we look the energy versus momentum diagram of GUN diode, actually some semiconductors, generally semiconductors have a valence band and conduction band, and energy band diagram is two valleys, the valleys come together, the conduction band lower part and valence band upper part, they come together, that gap is called the energy gap. But some semiconductors like gallium arsenide, indium phosphide and cadmium telluride, these three they have in the conduction band they have closely spaced sub bands, closely spaced multiple energy valleys in the conduction band. So, you see here this is not in general we get only one, but here this in gallium arsenide we get these values are for gallium arsenide. So, what happens you see from what is the difference between these bands, their energy is more, but you see that x axis is momentum. So, momentum of the electron if it is here, that its velocity will be less, here also velocity will be less. So, when a DC bias is applied across the material, an electric field is established, that is okay. So, let us say this is a gallium arsenide thing, and at lower E field most of the electrons, because energy is small. So, we will reside in the lower valley gamma, but at higher E field as we go give more electric field, that means if we go on increasing the bias, the electrons will get energy from that bias and will be transferred themselves to high energy satellite valleys like L and X. Now, in higher valleys effective electron mass is higher. So, mass higher means they are obviously from the momentum you are seeing mass is higher. So, mass higher, now more mass electron has lower mobility. So, these bands the electrons mobility are less, and if you go higher almost they are immobile type of thing, and we know this famous thing Einstein's equation that conductivity is proportional to mobility. So, we can say that if electron mobility is less, their conductivity is also less. If the conductivity is less, then we can say the current will decrease. So, we can say that if we go on giving more voltages, bias voltage, there is a threshold. So, more voltage means more current. that was Ohm's law, but here you see above a threshold actually that energy transfer started taking place, transferred electron, they become predominant, and then we get that as we are going increasing V, it is no more Ohm's law, then it is basically an decrease in the current. So, that gives rise to this region, gives rise to the negative electron. So, we are getting that above a threshold there is a negative resistance. Now, Gahn saw this in gallium arsenide and could make out that okay, we can make a diode oscillator from this. So, that is genius. This is a construction of a Gahn diode. You see that, or sorry, I did not tell you the this thing. So, basically Gahn diode you have, it is you do not have any junction sort of thing, you have a gallium arsenide crystal, then you have N type this, only in the two sides you have two different higher dopings N plus region. So, whole thing is you see same material, only doping level at the two ends for making electrodes they are making it different, but you are connecting when you are biasing, connecting positive part here, connecting negative here. So, this will become cathode, this will become anode, that is why it is called a diode. Otherwise, Gahn diode is not a diode, it is a bulk semiconductor, there is no junction concept here, no junction, but cathode and anode, so diode. At threshold voltage, E field is 3.2 kilovolt per centimeter for gallium arsenide, for other two materials it is different. Now, you see this is the anode metal, then N plus substrate, then active N layer, this is the actual bulk semiconductor, its thickness is 10 micromillimeter for a 10 gigahertz diode, N plus layer, then there is a again metal, here written silver, but copper also is used, cathode is here, here metal contact. Now, gallium arsenide is basically its conductivity is poor. So, lot of heat is generated in the device, its heat dependent, it is a poor conductor of heat. So, and that is why this this metal contacts they should be put to a heat sink, so that this heat can come out of this device. Now, equivalent circuit of a Gahn diode, again you see the junction, capacitance and resistance of a diode, only change here is instead of R j it is a minus R j, because we have seen the negative resistance, then there are the R s and L p, that thing, and then C p. So, R s lead ohmic contacts, bulk resistance of diode, and C p and L p are the package inductance and package reactance. Negative resistance typically of the order of -5 to -20 ohm. Now, let us understand the modes of operation of Gahn diode. There are two principal modes of microwave oscillation. One is called transit time mode or TT mode, another is called limited space charge mode or LSA mode. But there are also two special modes. Generally, these first two are the principal modes, but you can also operate it in two other special modes. One is called quench domain mode, another is delayed mode. So, there are 4 modes, out of that 2 are principal. We will see this all these modes what is there. So, let us see the TT mode first. So, we have this semiconductor material and that is biased and then connected to an RF circuit. So, this is the Gahn diode. Now, this side is since negative, so it is cathode, this side is anode. Now, when applied bias voltage is beyond the threshold voltage in the IV curve. So, what happens? That time we have seen that electron starts getting transferred. So, electron transferred to nearly zero mobility subconduction band. So, since they are immobile, so the electrons which are coming from cathode, now they starts becoming in a group, that group is called domain. So, heavier electrons bunch to form electric field dipole domain near the cathode. So, near the cathode you see this black one, we are calling this is a domain. Okay. So, like initially when the bias field is not there, the domain was here, that we will see later, but now there is a domain created. That domain is moving with a very small velocity, field domain near the cathode. Since external applied voltage is constant, now this applied voltage is constant, because beyond threshold we are trying to see what happens. E field across domain is higher than the rest of the crystal, because here the E field will be higher, here because the total voltage is same. So, here so many electrons. So, their electric field is more than this. So, that electric field higher, that means that is opposing this V. So, that is creating prevents further domain creation. Now, the domain is obviously it has a drift. So, we have stopped it, but that there is some small velocity. So, it is drifting with that lesser velocity, and other lighter electrons they drift with higher velocity. So, they are going. Now, current in presence of domain decreases, because current means with velocity, if the velocity is less, so current is small. So, that we have already seen from the IV curve also. After the domain travels to anode, then you see that current returns to higher level, because now the anode is here. Now, whatever electrons they again a domain will be formed here, that domain will start move. So, each domain basically when it gets connected by anode, we can say that it creates a pulse of current at the output RF circuit, where when the anode is getting suddenly you see a lot of current is there. Otherwise, the domain is taking quite long time to come. So, no current, but then suddenly a huge current. So, RF circuit, see obviously the other electrons they are few, some current is there always, but this is a pulse type thing over that. So, you get a pulsed signals. Each domain results in a pulse of current at the output RF circuit. Time period of that is equal to domain transit time, the domain from here to here, whatever time it takes. We are fortunate that transit time of this GaN diode for the domains that falls in microwave region. That means, in the microwave frequency, so 1 by that frequency, and this transit time is fortunate. So, that is why we get microwave radiation, microwave signal from this GaN diode. So, TT mode has low efficiency, as you are saying that you need to give the voltage and that much current you do not get. Frequency cannot be controlled. So, there is no controlling mechanism in TT mode. You cannot control the output frequency, whatever the transit time of the domain, by that only you can have this mode. So, this is the basic mode of GaN diode. Now, what is a LSA mode? Here we do some external thing, we connect that GaN diode to an resonance circuit RLC. So, GaN works as a part of resonance circuit. Now, resonance circuit frequency is much greater than TT mode frequency. So, whatever the GaN diode was producing in TT mode, the RLC circuit, the resonance frequency is much higher. So, here what happens, that means the this resonance circuit, that means its frequency is much higher, means time. So, only part of that domain transit time, by that one signal is coming. So, the domains they are not being able to form, do not have sufficient time to form, because this frequency is much higher. So, because domains require some from electrons to domain creation, that takes some time, by that time the whole thing is again repeating. So, domains do not get created in the LSA mode, limited space charge mode, that is why they are called that. You are not applying the space charge to develop. Applied DC voltage is greater than threshold, and in the middle of IV negative resistance zone. So, you see that the V is not VTH, you are applying almost here VTH, and RL you are choosing, so that oscillation can start. Steady state, after at steady state RL becomes equal to RG. So, there is a steady sustained oscillation takes place. Now, peak to peak voltage of microwave oscillator equal to voltage range of negative resistance curve, because this to this voltage range of negative resistance curve, that is equal to the peak to peak voltage of microwave oscillator. Power efficiency is 20%, output power several watts, power decreases with frequency 1 watt at 10 gigahertz. If you want 100 gigahertz signal, then several megawatt, but this is a good mode of operation. Now, quench domain mode, resonance circuit tuning frequency is slightly greater than TT mode. In LSA mode it was much higher, here it is slightly higher than TT mode. So, dipole will be creating here, but dipole domain is quenched before it arrives at the anode, because already when it is arriving the resonant frequency is higher, that is why the already a negative swing has taken place. So, it will not be, so we say that the domain is quenched, but it will have some otherwise TT mode some operation. So, there will be current, but it is a quench domain. Then delayed mode, resonant circuit frequency is less than TT mode. The other option, that in quench domain mode the resonant frequency is slightly higher than TT mode, here it is slightly lower. So, dipole domains arrive at anode well in time, then they will have to wait, because formation of a new dipole is delayed until the oscillational voltage increases above threshold voltage. So, here the mode that will be slightly delayed, because after creation of a domain, the domain is arriving, getting a pulse, but then again some time, then the whole operation again is starting. So, Gunn diode oscillator, generally this whole RLC circuit, that is called Gunn diode oscillator. Gunn diode is mounted at the center, you see this is the Gunn diode perpendicular to the broad wall of the guide. Broad wall means the we seen that what is the broad wall. So, perpendicular to that the of a rectangular guide, maximum E field of T N mode is there where it is placed. Intrinsic frequency of oscillation is V d by L, drift velocity of domain by effective length. This is the intrinsic frequency or the TT mode of operation frequency. For gallium arsenide, this V d drift velocity of domain is typically 10 to the power 7 centimeter per second. Cavity is tuned to F naught by adjusting the short position. You see this is the short. So, if you move that short, you can make the cavity frequency. A tuning screw is inserted perpendicularly at the center of the broad wall for again fine tuning. External load 20% higher than RG. This 20% is a good one, because when the actual sustained oscillation is taking place, this load is reduced, because the RJ is a negative value. So, RL and RG combination, that will have to be balancing. Gunn diode is placed on a metal post, top of the post, as we have seen. Gunn diode is, this is the post. Post means that has some inductive value insulated from waveguide to form RF bypass capacitor. So, top of the post is insulated. So, there is an RF bypass capacitor also. DC voltage is applied to the post. So, it is at the DC voltage goes through here and the RF is choked. Inductive iris dimension controls degree of coupling to external waveguide. It is, see, this is the iris. So, whatever this oscillator is producing, the external part, iris means it is a capacitive thing. So, from there by capacitive coupling it is taking to the outside RF. Now, gun diode oscillator is in laboratory instead of reflex klystron, we have gun diode oscillator, then this is producing microwave signal and that external load I said DC voltage, this I said, output power is few watts you can get, like klystron you can also have this gun power, gun diode power, pulse power output 100 to 200 watt pulse power you can get, bias voltage 10 volt, bias current 1 ampere. So, quite good, you can by 10 volt supply in laboratory we can have that, frequency 8 to 40 gigahertz you can get, frequency tuning you can get electronic tuning 2%, okay, quite at gigahertz range 2% means suppose 10 gigahertz. So, you get 200 megahertz, that is quite good. Power output limited by heat dissipation difficulty of small diode chip, gas is a poor conductor, that is why there. So, the power output, so you cannot go on increasing very high power because heat dissipation is a problem in the gas, etc. Advantage is small size, ruggedness, low cost. This is a typical gun diode oscillator you see. So, this by moving this screw you are basically you can change the tuning, that this is the, you see the tuning screw and this is the iris from where power is extracted and this side actually fits into the gun diode oscillator. Now, we will see another diode, actually there is another effect, avalanche transit time devices. GAN we have seen that transfer electron type, but avalanche process that also give a good transit time devices, those are called ATDD. They have three varieties. Inventor was W.T. Reed in 1950, almost the much 4 years before the GAN invented that GAN diode. These are p-n junction diode, these are junction diode with highly doped p and n regions. So, p-n junction diode with highly doped p and n regions. This also produces negative resonance at microwave frequencies. This operates under reverse bias condition. So, it is a reverse bias diode and give sufficient reverse bias, so that avalanche breakdown takes place. Now, there are three varieties of ATTD. One is called impact ionization avalanche transit time. This is having 3% efficiency up to 100 gigahertz, 1 watt power output. So, quite good low frequency thing. Trapped plasma avalanche triggers transit, trapper diode, low frequency, these are low frequency diodes 1 to 3 gigahertz only, and barrier injected transit time buried diode. This has low noise figure less than 15 dB, low power, low bandwidth. Actually, these ADTDs they are generally having high noise figure because these are avalanche processes, lot of noise, but this barrier injected transit time this has low noise figure, but 15 dB is also not a very good noise figure, but in this family it is a good one. So, this is a thing you see that N plus P junction, then there is an intrinsic junction P, also you can have other varieties P plus etc., but there is a p-n junction you all this see. So, material you can have germanium, you can have silicon, you can have gas, you can have indium phosphide. Now, gas provides highest efficiency, highest operating frequency and lowest noise figure. So, impact diodes with gas is good, highest. Now, operation it is a reverse bias operation. So, you have a junction diode, when reverse bias is greater than breakdown voltage of N p-n junction, then high field in junction as shown, that electric field is high. So, with this high field there is sufficient energy, high energy. So, holes in since we are describing with respect to these. So, holes acquire sufficient energy to tear valence electrons of atoms and bring them to conduction band. So, then these now again these electrons with such high energy, they will collide with other atoms, they will take that is the avalanche process, onset of avalanche multiplication of electron hole pair. Avalanche process creates noise, that is why you see noise figure of IMPACT diode is 30 dB. So, very noisy, but it is a good that in if you want to have power, you can also use IMPACT diode. Thank you.